Great. Well, thank you, Meming, for that warm introduction. Also, thank you so much for the invitation. It's a real privilege for all of us to be able to share this work that our team has done on building neuromotor interfaces. As Meming said, I come here to you from Meta. Many of you probably know Meta from its family of apps, like Instagram, Facebook, WhatsApp. But there's also a division at Meta called Reality Labs. And Reality Labs makes hardware. It makes hardware for what it views as the next generation of computing. So these are things like the Quest VR headsets, like the Ray-Ban glasses. And then about 6 years ago, Reality Labs acquired a startup known as Control Labs. This was founded by a number of Columbia neuroscientists. And Control Labs focused on what the input would be for the next generation of computing. So it's been said that every phase of computing has a different set of really canonical inputs, right? So the desktop computer had the keyboard and mouse. The phone had multi-touch. These Quest headsets have these handheld controllers, and so on and so forth. And so the mission of Control Labs was to find, OK, what's going to be the next thing that we use to control computers? Now, I am an aging millennial. And for us, neural interfaces were thought to be sort of the ideal form of computer input. So for those of you that have seen this movie, The Matrix, here people insert their brains basically through jacks into a sort of cyberspace and use that to gain sort of superhuman abilities where they're not bound by the constraints of the flesh, so they can fly and they can exceed what's possible with normal biomechanics. So for computers, the thought is that neural interfaces could enable you to have a higher bandwidth connection with computing devices, right? So if you take the signals in your brain, in a typical fashion, we have to use these signals to control our bodies. We use our bodies to control the sort of limited bandwidth of these input devices to eventually interface with a CPU. And the idea is, well, maybe we could directly interface our brain with these computing devices, avoiding some of the bottlenecks that we find in the biomechanical plant or with the limited set of affordances that you find in these interfaces. Now, of course, this is not a new idea, right? There's many different types of neural interfaces that have been introduced. And so in recording from the brain, we have intracortical recordings like a Utah array, like ECOG. And these have, of course, produced really miraculous results in some cases. They offer high bandwidth, they offer high signal, low latency, but they're invasive, right? They require neurosurgery, which has many associated risks. There's fundamental challenges in recording from the entire brain. How much brain can you really interface with? And I would say to date, they've really resulted in single participant models, right? And so in a typical setup here, you would take an individual, you would ask them to say, imagine reaching for a cup 100 times, 1,000 times, and then you would train a decoder from that patch of brain that you're recording on a given day to perform that action. So there's a lot of calibration that is required to use them. There's also, of course, EEG, fMRI. These approaches are notably non-invasive. They allow you to record from a much larger amount of brain, but they're much lower bandwidth, they're much noisier, they're much slower, and the equipment is somewhat cumbersome. So the approach that I'll tell you today is not a neural interface and recording from the brain, but it's one synapse away. So after the spinal cord, spinal motor neurons send their outputs to muscles. The motor unit action potentials are amplified in the muscles, right? And so hundreds or thousands of times. So you get very large amounts of signal, electrical signal, that come through your muscle. And you can record these signals with a technique known as electromyography. In this case, we'll be talking about surface electromyography, where you have a band, just electrodes on the surface of your wrist. And so surface electromyography is non-invasive. It gives you high signal, low latency, much like intracortical recordings. It offers a sort of intermediate level of bandwidth where you get this very high precision, but maybe not as much richness as you're seeing in the signaling of the brain. But previously, I would say in the era before Control Labs, the equipment for doing surface electromyographic recordings was somewhat cumbersome. So you could see, you could have a sort of wet gel preparation like you might find in a lab, where you take someone's arm, you might shave off all the hair and attach some gooey electrodes. There were early consumer versions of this. Oh, let's see if I can go back. That you can see here. It's sort of chunky. And similar to intracortical recordings, these had really been demonstrated in a single participant setting, right? So you take a person, you attach all these electrodes, you ask them to do a number of tasks, you train a decoding model on that specific person. And so what was set out to do at Control Labs, and what I'll be talking about here, and this is published work, is how we overcame that issue to build really generic models that anyone could use, where you just take a surface electromyography band, you put it on, and you use it to control a computer. And I would say, like many applied machine learning problems in industry, the solution to this is a mix of fundamental science and machine learning, as well as a really well-oiled data and modeling flywheel, right? So where you have to build a system to collect large amounts of data in class of interest. I think, much like the previous talk. And so this is really a story in 3 parts that I'll briefly touch on. So hardware, we need to build better hardware than what was there before. Software and recording infrastructure, where we need to be able to use these devices to record data at scale. And then, of course, modeling to be able to exploit this data. So I'll start with hardware. So as I mentioned, there are precursors to this approach. SEMG neural interfaces are actually very old. They started right after World War II, when there was a lot of need for prosthetics. And so there were actually early electromyographic prostheses. There's a Boston arm, which I'm from Boston. I'm a big fan of. But they're still fairly cumbersome. And you can even buy commercial neural prosthetics that have SEMG, but they haven't had good traction in the market, I think, because some of these decoding models are not as robust as they need to be. They require a lot of calibration. They put a lot of burden on those users. And so the innovation here started with a sweatband with a number of electrodes. But over time, probably connected to some external amplifier that you can't even see here, it became more and more integrated in a much sleeker form factor. Here you can see the computing devices is now just in a single box. You can see now there's just 2 devices that you could imagine both putting in an arm. Here they've been integrated into a single device. And the device that I'll be telling you about today, the sort of research workhorse for this, is the SEMG research device, which you can hear has a much sleeker form factor. There's 16 bipolar channels that you can see arranged around the wrist. There's a common ground in between them. And then a kind of compute core here that is streaming Bluetooth to a PC. Now, this band offers very high signal to noise, and it's easy to take on and off. So I'll just tell you, there you can see this person taking it on and off. You can see a high richness of the signals coming off this band when they're moving the device. It's really an amazing intricacy that you see in these patterns. The reason taking it on and off is important is to build models that generalize, right? Every time you take the band on, put it off, you're sampling a slightly different set of recording sites. And so to be able to train models for a person to just put the band on, control computer, you need to be able to generalize over that. The resolution is also quite good. So as I mentioned, there are fundamental quanta, the motor unit action potentials that make up the surface electromyographic signal. And here we can resolve these putative mu-aps. We're not doing paired recordings, but you can see we can have a very, and this is repeated instances, just threshold crossing of several of these that you can record just with this dry electrode band. And I just want to emphasize, before it was, I think, maybe, I don't know how widely held in the field, but you really needed kind of these wet gel interfaces. You need this tight coupling to the skin to be able to get this level of resolution. Now, I think what you can see with this band, so I mentioned that you have this really rich level of signal. So this is, you can see a video of a person performing a series of different discrete gestures, the task I'll be focusing on for the next few minutes of the talk. And so they're controlling this little video game character here with a series of swipes or taps. And here is a set of reconstructions, middle pinch, holding their middle finger down, pinching their index finger, swiping with their thumb in various directions. And you can just see intricate patterning of the signals across these. Now, what we can do is we can take average waveforms, neuroscientists at work here, across these different gestures. And so what I'm showing you is each of these rows is a different gesture. So index pinch, swiping your thumb out or down. Each column is a different person performing these gestures. And I think what you can quickly appreciate, say even just taking a look at this row, is these waveforms are very different, right? So people have very different temporal extents. There's like, this is a multiphasic pattern versus kind of more of a uniphasic pattern. This one is much longer tail. These different shaded lines are in different cases where people put the band on just different times. And so again, like these different sessions make a difference. And I think what this highlights is, the challenge of getting a model to generalize, right? People have different behavior, they have different anatomy, they have different physiology, and so you need to really collect data at scale to be able to generalize across all of these different cases. So, the second part of this is high throughput data collection. And what I won't be talking about is really software engineering. There's a huge amount of software engineering that lies behind this work in just like building machine learning frameworks that can record data from the band and run models with low latency. But what I will talk about that I think is pretty germane to this neuroscience audience is the importance of these automated data collection paradigms. This is something I experienced in my postdoc with rats, but you can see here our typical setup for recording data is you have a person in front of a computer. They're asked to perform a series of gestures, like keep focusing on these like discrete gestures, these pinches and taps that I talked about before. And you can see another example of this here, where this person has scrolling bars that are drifting down the screen, and then they're being asked to either pinch their index finger or middle finger. You can see they're getting closed-loop feedback when they complete this gesture, so they're getting some feedback in pink. You can tune the statistics of which gestures they're using, the inner gesture timing. You can add some randomness to this, all with the idea of gaining generalization of these models to these variations in timing that you might encounter. And then during this talk, I'll talk about the size of the data, right? So part of this is it's automated, right? You can just have a number of people looking at laptops, performing gestures with minimal supervision to gather this data. And I'll be showing you data, models that were trained on somewhere more than 10,000 people. And again, diversity is key to covering the population. And so, here we sample from a broad range of a variety of different demographic characteristics, from wrist circumference, age, BMI, height, handedness, and also behavioral characteristics like their typing speed or exercise frequency. And then the final part of this is models, right? We need to build models that can generalize over people to decode tasks of interest. And so I've talked about this discrete gesture task where we're having people like control this video game character and perform a series of gestures. Also be showing you results from more continuous control here using wrist angles, and also handwriting, which sort of still incredible to me that this works. But you hear a person is just asked to write without a pen in sort of their natural style to write different text. And so you could see a closed loop model running here, writing the laser printer is jammed. And there's a few different types of models that we are using here. They all have the same flavor that are probably familiar to many of you, where you take EMG, you pre-process it with some set of featurization, either with raw signals that are just, say, lightly high-pass filtered, or taking a covariance matrix and maybe power spectra on top of that covariance matrix. You'll get out a set of features, like here you can see these covariance matrices that I mentioned. You apply it through a different kind of deep learning model. So LSTM, a time-depth separable network, which is kind of more parameter efficient for sharing data across channels and time. A conformer, which is a streaming analog of these transformers that's common in audio processing. Then we post-process the signal before giving an output command to a computer or input to a computer. And I should mention that as part of this paper, we have released data sets and also modeling pipelines for each of these different tasks. And so there's 100 participant tasks, which are, I think, some of the largest available for SEMG. And also example modeling code to be able to run these with the hope of interfacing more deeply and spurring innovation in the academic community. And scale, the hypothesis here was that scale would drive these improvements. And this slide is for Meming, the little log plot. Is it a power law? Is it not? But so, what's been found empirically in the case of many different types of transformer-based models, so large language models, vision transformers, is that the model performance is scaling rationally as a function of data set size, right? So that you can predict how to go from GPT-3 to 4 to 5 as a function of the amount of data or the amount of compute or the capacity of models that you put in. And so I think the hypothesis here was that these same scaling laws would apply to biosignals, which is not really obvious, right? These are like very, on the one case you have like internet scale data. You could imagine it being, having particular noise characteristics or distributional characteristics. And so it's like not obvious that these same types of, let's call them power laws, will apply to biosignals collected from humans. And so, I'll show you, here's this discrete gesture task. And if we look here at the classification error, so the error that you're making in gestures, this is in an online closed loop, or no, this is actually offline setting, excuse me. Then we can look at this as a function of the number of training participants in the model. Again, log plot. And so, as we go from 40 to 80, we see a decrease. As we go from 80 to 160, so as we keep doubling the amount of data, we're seeing reliable decreases in the error of the model. And going all the way here past 1,000, you see we're getting below 10% classification error rate, going 2,800, all the way, in this case, to almost 5,000 participants. And you're seeing this really reliable scaling of performance, where here there's a power law fit shown in the dashed lines across many, many orders of magnitude. So, 2 decades in this case, many doublings. And, there's no sign that this performance improvement is saturating, right? So you would see continued scaling if you went probably to 10,000, I don't actually know, but 10,000 or 20,000 or so on and so forth. And then you also see scaling based on model size, right? This is another characteristic of these deep learning models, where as you increase the capacity of the model, you're also seeing improved performance. Risk control, similar phenomenon, right? So we're going here, a smaller amount of expansion, but so from 20 participants to 40 participants to 80 to 160. Again, reliable improvements in the decoding model as a function of the amount of data. And then handwriting, again, and handwriting, this is a task that I had, I did not think that this task would work. It's, of course, a more than 26 character classification task when you think about adding punctuation in. People have incredibly different styles of handwriting. Like, I get letters from my aunt every year, and I cannot read them one bit. And, so again, we're going here from 25 to 50. It's starting with very, very poor models. I mean, I think I was right for being biased against this. So you take 25 people, which in academia, that's like a pretty good sample size. But you would still see 50% classification error. And so maybe not surprising that my prior coming from academia was like, well, this is probably not going to work. But then as you go to 100 to 200, you're now maybe more down in the 20% error rate. It's still not obvious that these scaling laws for our LLMs are going to apply here. But it just keeps going down. So here at 1,600, you're now more in a 10 or 15% character error rate. 3,200, and then for this particular data set, 6,500. And you can see for the largest model, the 60 million parameter model, we're now getting almost 7% character error rate, which is, I think, pretty amazing. It allows you to get this sort of really accurate closed-loop performance that you can see in the example here. And the thing I'll add is that you can use personalization, so data from within a subject, to improve these more. And so again, this 50% character error rate trained on 25 participants, so kind of a characteristic regime from before would be if you added 20 minutes, so each of these different lines and each of these different colors is a different amount of personalization data. And you can see you can get these improvements. But so here you're almost doubling your performance. You're going from 50 to 25. But if you get to 6400, personalization matters much, much, much less, right? So the more generic pre-trained data you have, the less that fine-tuning matters. And so here you're going maybe more from a 9% CER to 7%. And so personalization is less and less important, at least for a given fixed amount, as you go into these more generic regimes. So this was a research paper that introduced this research device and these computing models. I'm also happy to announce that this is now a product. And so if you are in the US, I don't think this is available in the European Union quite yet, but if you're in the US, you can go to Best Buy. You can go buy this neural wristband that was just released, I think, a few weeks ago, maybe September 30th. This is a pair of Dan's in the audience, his glasses. And so you can pair these bands with these glasses, and there's a little heads-up display that will pop up, and you can use the band to control aspects of that pop-up display. And then these glasses are also, you can take pictures and listen to music. So I want to spend just a couple minutes talking about the future of SEMG. And so there's a couple types of higher bandwidth interactions that we can do. So I think handwriting was a real clue that this sort of recipe of scale and high precision hardware can open up new frontiers. And so we had a couple papers at NeurIPS, I think it was last year, on 2 higher bandwidth tasks. So continuous pose estimation. This is a subject close to my heart, coming from pose estimation in animals. And so here we had people in motion capture arenas collecting the full kind of 22 joint angles of the hand. And so you could see here's a ground truth recording of the hand pose. Here is the reconstruction just using one of these neural wristbands. You can see you can get, I would say, pretty good accuracy. And this, much like the other data set, is open source. And so we have data sets of about 200 participants across almost 400 hours for that data set. We also had a typing task. So this is EMG to QWERTY. And so people are typing on a screen, typing on a, I think, Mach keyboard, or even just on the kind of relative to home keys. And you're, actually, this is a keyboard. And you're sort of able to reconstruct the types of characters that they make. And again, this is available on GitHub and is open source. What I've shown you is mostly kind of like overt movement that SEMG is being able to use to control. But the hope, and so kind of here where you're actually controlling a physical plant, the hope by recording from these muscles is that you can enable a more intermediate level of bandwidth, right? So there's types of isometric interactions, right, where it's like I'm applying a lot of force here. You should be able to detect this if you're recording for muscle activity, even though it's not an overt movement. And there are, of course, examples of this that we can detect. So here's at this point, a somewhat old one, but I think it's a very nice example of the idea. So a person there is pressing a spacebar to control, and then now they're controlling it with just very subtle movements of their index finger, and doing so across a variety of different postures with their arms folded, with their arms in the pocket, and so on and so forth. And then finally, I think probably, to me, maybe the most exciting application of this work, let me mute this, is work for accessibility. And so this is a collaboration with CMU and Doug Weber's lab, where people are using these individual motor units detected with the SEMG wristband to, in this particular case, control this video game character. And so in this setup, people who have spinal cord injuries often have residual motor units left, right? And so even though they can't overtly move their arm, there's still some residual signaling that is present. And so as again, coming back to these putative motor unit action potentials that you can detect, you can have training paradigms that will allow you to rapidly detect a particular motor unit action potential and build game controllers based on that experience so that people with these spinal cord injuries can control these games, can gain a really meaningful level of control that they did not have before. Using these wristband devices with, again, kind of like minimal calibration and setup, and of course, without any invasiveness. This is a second example that I really like here because I think it kind of, let me see if I can get this to play. I think highlights kind of some of the social benefits that can come from these games. Where now here this patient is playing a game with his mom. His mom is on the top, and she is actually not very good at Mario Kart. He is much better at Mario Kart, but he is controlling it here with this SEMG wristband, again, based on doing this kind of motor unit level control. And so not only, kind of like meaningfully restoring an ability to engage with computers, but also, more generally, socialization, which is, of course, incredibly important. And so with that, I'd just like to thank the research team. I'm here as just like an emissary, I think, representing a huge number of people, both scientists, many of whom neuroscientists that you all probably know, have trained in similar places, similar labs, engineers, as well as technicians, design specialists, product engineers, industrial engineers, and so on and so forth. And I'll also note that we are, I think, currently have calls open for internships, and then occasionally have full-time roles in New York City or the Bay Area that you can find on Meta or on LinkedIn. And so with that, thanks.